folks. Welcome to
Vector calculus.
Alright folks, welcome back to the next lecture in vector calculus. Today we're checking out this problem, alright? What's our problem today? Let's check it out. Find the line of intersection between two planes. How do I know that these are the equations of planes and not lines or points or vectors? Go ahead and check out the last lecture to find me review that, alright? So, I have two planes and I want to find the line of intersection between them. Well, first thing I want to do, as always, as you know, is to draw a picture. Alright, so what do I mean by two planes intersecting at a line? Well, hopefully you remember that two lines intersect at what kind of geometric object? Well, they intersect at a point, right? What about two planes? Well, to answer that question, just look at your living room, right? Look at your living room and you'll find two walls. And the two walls look kind of like this. You got one wall standing upright, and you got the other wall kind of slanted, kind of oblique. And so these two walls are just like planes. And where do the two planes meet? Well, you can clearly see it. They meet at a line. So two lines meet at a point, two planes meet at a line. Let me go ahead and write that down. Two lines meet at a point, meet at a point, and two lines meet at a line, or rather two planes meet at a line. Two planes meet at a line, Alright, so you can see that kind of interesting pattern there. You got two lines meeting at a point, two planes meeting at a line. Who knows, maybe two spaces, two three-dimensional spaces meet at a plane. Who knows, just speculating. Okay. So enough of that. How do we find the plane? How do we find the line of intersection between two planes? We know that to find the line of intersection between two lines, I'm mixing up all my jargon. To find the point of intersection between two lines, we have to set the two lines equal to each other and solve for x. How do we find the line of intersection between two planes? Well, let's go ahead and check it out. Instead of telling you, it's much better to show you. So what am I going to do? First thing I'm going to do is just play around with the equations. Okay, so let's write down the equations. We got x minus 2y plus z, x minus 2y plus z equals 0. And what's our second equation? 2x plus 3y, 2x plus 3y minus 2z equals 0. Alright, so we got two equations and we want to find the line of intersection between these two planes. Now the line of intersection between these two planes must satisfy x, y, and z values that are true for both planes, right? So just like regular two-dimensional lines, what we can do is just isolate two variables, right? So what we can do is multiply this first equation by 2, or rather negative 2. Wow, my marker could not have found a better time to die on me. Well, that's good because I got two backups, ladies and gentlemen. I have come prepared for this moment. So let's multiply our first equation by negative 2. So we get minus 2 times x minus 2y plus z equals 0. Now why am I multiplying my first equation by negative 2? Well, it's kind of foreshadowing something. It's foreshadowing the fact that if I multiply this by negative 2, my x terms will cancel out. I'll just be left with y and z and y and z. And then you can see where I take it from there. So this is going to become what? Well, I'll end up with minus 2x plus 4y minus 2z, and that's equal to 0. And now I can add it to my second plane, 2x plus 3y minus 2z equals 0. Well, this is unfortunate. My first whiteboard is blocking, but that's okay. Let's put this guy away. Okay, so if I add these two guys, I'll end up with x just getting out of there, and I'll have 7y minus 4z on the left hand side. And so my y is going to equal 4z, and so y is equal to 4 over 7z. Okay, and now we can go ahead and plug this back over here to get x in terms of z as well. So we'll have everything, x, y, and z, in terms of one variable. So plug y equals 4 over 7 back over here. So 2x plus 3, and not y. Instead of y, we'll put 4 over 7z. 4 over 7z minus 2z equals 0. And so 2x plus 12 over 7z minus 2z equals 0. So 2x is equal to what? Well, on the right hand side, we'll have minus 12 over 7z plus 2z. Okay, and of course, instead of 2 over here, I can rewrite 2 as 14 over 7z. And what does that become? Well, I'll be left over 2x is equal to 2 over 7z, and that will finally reduce to x is equal to what? X is equal to 2 over 14z. Wow, what a hassle. Talk about a hassle. All right. Well, now we get x, y, and z all in terms of one variable, and that variable is z. So I know that x is 2 over 14, or just 1 over 7z. 1 over 7z. I know y is equal to 4 over 7z, and I know z is just equal to z. Now, here comes the magic part. Well, the easy part actually. Just let z equal t. T is the parameter, so why not? Let z equal t, and so we'll end up with our line almost. X is equal to 1 over 7t, y is equal to 4 over 7t, z is just equal to t. We're almost there, except for one important thing. What is that important thing? Well, you might realize that we missed the constants, right? If you recall the equation of a line in three-dimensional space, we have these constants, x naught, y naught, z naught, right? Where are my constants at? Where are my constants at? Well, if you look at these two planes, they both pass through the origin. They both pass through the origin, and we know that because their d values are 0. And so our x naught, y naught, and z naught are just all 0, right? And so this is the equation of our parametric line that we're going to be left with. X is equal to 1 over 7t, y equals 4 over 7t, and z is just equal to t. And of course you can, write this in symmetric form as well. I'll do that for my die-hard symmetric fans. So I don't know what else to say. T is equal to z. And of course this is going to be 7 over 4y. And of course that is going to be 7x. And that, ladies and gentlemen, is the symmetric form of my three-dimensional line. Here's the parametric form of my three-dimensional line. Here's the parametric. Here's the symmetric. And really that's all there is to finding the intersection of two planes in 3D space. We'll check you out in the next lecture of vector calculus.
Embedded plus MKO plus scaffolding equals learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.